So we've taken a rather detailed look at our sine and cosine graphs. So in this video, we're going to look at some of the applications of those graphs. Specifically, our objective: solve applications involving trigonometric functions and their graphs. And we're going to focus on sine and cosine. So what do we know? Well, we know that the graphs of y equals a sine of b of x plus c and y equals a cosine of b of x plus c have amplitudes equal to the absolute value of a, the coefficient, and have periods equal to 2 pi over b. And we're going to focus on motion. Simple harmonic motion here. What is simple harmonic motion? Repetitive movement back and forth through an equilibrium or central position, so that the maximum displacement on one side of this position is equal to the maximum displacement on the other side. So let's take a look at this. We're going to map out here over time the height of where the radius hits the circle. Okay, you'll notice at time 0, where it's here, at 1 unit of time, it goes up a little bit. Here it is in the height on the y, up a little higher to this height. It maxes here. There's your maximum height. And then as time continues, it comes back down to 0 here. And then it goes down to a bottom point here, and then it comes back up to 0 here, and it just continues. So the maximum displacement on the upper side, in this case, on the higher side, is equal to the maximum displacement here on the other side, in this case, the lower side. Okay, another piece of vocabulary for us, another definition. What is angular velocity? Angular velocity is how fast an object rotates or revolves relative to another point. In other words, how fast the angular position or orientation of an object changes with time. How fast is this angle moving? Okay, how fast is it going to force this up and down going on here? It's often designated by the Greek symbol omega, which is kind of the script W, and it is measured in radians per second. So we're going to want to make sure to have our calculators for graphing purposes in radian mode. Let's make sure I do that. Okay, so we have the simple harmonic equation. Get myself straightened out. Okay, simple harmonic motion is given by the equations. Well, the displacement is equal to the radius times the sine of the angular velocity times time plus the vertical displacement, the initial vertical displacement, or the displacement is equal to the radius times the cosine of the angular velocity times time plus the vertical displacement. Okay, so I just defined these here. This symbol here is the Greek symbol for phi, right there. The kind of a circle with a slightly slanted line through it. Note, if at time 0, the displacement of the projection is 0, okay, then we're going to use the sine function in general, okay? Otherwise, we'll make use of the cosine function. Just a general statement there. A couple of examples are going to help us. Keep my Desmos turned on here. Okay, I want to make sure I keep that equation. I'm going to make use of that equation. I'm going to keep those equations up here. A riverboat's paddle has an 18-foot radius, and it rotates at 26 radians per second. Find the equation of motion of the vertical displacement from the center of the wheel of the end of the paddle as a function of time if the paddle is initially horizontal and moves upward when the wheel begins to turn. Sketch 2 cycles. Okay, well, let's just take a look at a picture of this thing. I'm not fancy. I am not the best artist. But we have a center of a wheel. We have a paddle coming off that center. There you go. There's a good paddle. Look how fancy that is. We know that paddle has an 18-foot radius, and we know that its angular velocity is 26 radians per second. We know that it started. We're looking at the end, so we're going to go from here. We're going to follow this around, and then back down, and then back around, and then back up. And we know the paddle is initially horizontal. Okay, so initially horizontal is going to tell us that at time 0, the displacement is 0. This initially horizontal piece, and then it moves upward. This is saying to use sine. Okay, and our vertical displacement, well, if it's initially horizontal, the vertical displacement is 0. Okay, so let's take a look. We're going to use the sine function. So our displacement is equal to the radius times the sine of the angular velocity times t plus phi, which is the vertical displacement, which is 0. Okay, so that tells us the radius. Whoops, I meant to fill this in. We know the radius is equal to 18 feet. We know the angular velocity, omega, is equal to 26 radians per second. And we know that our vertical displacement, initial vertical displacement, is equal to 0. So this leads us to the equation for simple harmonic motion. D is equal to 18 times the sine of 26t plus 0. I'll just go like that. Okay, so there's the equation. Now let's draw two cycles. We'll do it on Sketch, and then we'll take a look at it in Desmos. Assuming I can keep my Desmos on. Okay, so let's see here. In order to draw a picture, what is our amplitude? Well, the amplitude is equal to the absolute value of A. In our equation, A is 18, so it's the absolute value of 18, which is positive 18. And I can make that 8 look a little more like an 8. That's better. So here's my picture. I'll go as high as 18 and as low as negative 18. That's the amplitude. What's my period? Okay, well, the period is 2 pi over b. B is 26, so it's 2 pi over 26, which is the same as pi over 13. Okay, if we want to look at that as a decimal, pi divided by 13 is approximately 0.24. Okay, but we want to sketch two cycles, so we want two cycles, or two periods, which means we want one period times 2. We want to go to 2 pi over 13. Okay, so one period is pi over 13. I'll put it about here, pi over 13, and then I'll see if I can't just kind of sketch and match that distance. Here is 2 pi over 13. And I need to get my picture a little clearer for you. That's better. We know it's a sine function. We know one period is going to be between here and here. So I'll go up, come down halfway, go down to negative 18 and come back up. There's one period taking place in a pi over 13 space, or distance. And then I'll go up, I'll come down, and there are two cycles. I'm pretty close, so yeah, I'm pretty close for hand drawn. Two cycles of this function. Okay, let's take a look at that on Desmos. Now I kind of set up my Desmos, so I'm going to need to, I may want to go back and kind of unset it. So let me go back and, let's go back and go from negative 10 to 10. Okay, I'll go, well, let's see, I'll just go home. How about that? Yeah, I'll go into the home screen, I think. Okay, so I'm in the home. I just pressed home. Okay, I want to do it from the beginning. I was kind of practicing earlier. So go into here. Let's put in this equation. we'll use x and y. So y is equal to 18 times the sine. I can just type in sine if I want to. I can choose it from functions too. If you type in S-I-N, you'll notice it becomes in regular, it's non-italic. Okay, I want the the parenthesis, and we had 26 times t. Well, we're going to use an x instead. And look at that. Well, we know that our period was only a pi over 13 period. So let's go into the toolkit over here. So I'll press the tool. First off, I'm in radians, and that matters. Okay. Let's take a look. Our y-axis was pretty simple. Our y-axis went from negative 18 to positive 18 because that was the amplitude. I'll go from negative 20 to 20 so that we can get it included in the graph with a little space above and below. Our x-axis, well, we started at 0 and we only went to 2 pi over 13. Well, 2 pi over 13 is approximately, well, it's double pi over 13, which we said was 0.24. So double that to get about 0.48. Let's go to 0.5. Whoops, go back. I didn't switch it yet. So 0, go to here. And let's go to 0.5. There we go. Okay, so now, let me come in just a little bit, and you can see here we are. Okay, so we've done... If we tap our points, we'll see in radian mode. That one didn't do it. Am I in radian mode? Well, this one, okay. So these, they couldn't give you a precise radians, but there's the pi over 13 for one period. And we can see our maximum of 18 and our minimum down here, which you can't see because it's a little bit off the screen. Our maximum of 18 up here and our minimum of negative 18 down here. And there's the pi over 13 radius. And the same thing, that one might not give it to us. Nope, it doesn't do pi over 3 pi over 26, I guess. And then there is the 2 pi over 13 for the second cycle, 2 cycles of that function. There you have it in Desmos. Okay, let's do another example, and give me a moment to get my paperwork together. Let's see here, slightly different. I think we're still going to use the sine function, but a couple of other things to take into account here. Example 2. The motion of a piston of a car engine approximates simple harmonic motion. What's a car piston do? Up, down, up, down, up, down. So it does kind of have a central location, a high and a low, and the up to the high and the down to the low are the same distance. Given that the stroke, which is twice the amplitude, okay, well, if the stroke is 0.18 meters, and that's twice the amplitude is going to be this number divided by 2. The engine runs at 2,600 rotations per minute. Omega is radians per unit of time, so that's a little different here. The piston starts in the middle of the stroke. Okay, so we're going to look at the sine function. In the middle of the stroke, we're going to think sine because we're not at the top or the bottom. And we're going to know that the middle, our displacement is 0. So our phi is 0. Find the equation for the displacement as d as a function of t, sketch 2 cycles. We got a note here. Frequency is the number of cycles per units of time, which is right here, versus angular velocity, which is the number of radians per unit of time. Okay, there are 2 pi radians in one cycle, so omega is equal to 2 pi f. Omega is 2 pi times the frequency to get us back to radians per unit of time. Well, we know we're using the sine function, and our generic equation is the radius times the sine of omega. Remind me what omega was, the angular velocity, times time plus the vertical displacement. which we said we're in the middle, so our vertical displacement is 0. We know that omega is equal to 2 pi times the frequency right here. Well, the frequency we know is 2,600 rotations per minute. So 2 pi times 2,600, which gives us 5,200 times pi. We know that our phi is 0 because we're starting the middle of the stroke flat. There's no displacement. And we're going to do our r. And the stroke is twice the amplitude. So we have to take the stroke divided by 2 to get the amplitude. And the answer is 0.09. So 0.18 is 2 times this. Okay, we're in a good place. We have our equation because we have the value of our unknowns. D is equal to the radius, 0.09, times the sine of omega, which is 5,200 pi, times t plus 0. So we're all set right there. That's the equation. Let's do a sketch. Okay, so for our, let's keep my paper so you can see it. Okay, so we need to know amplitude. And we're going to look at the period. And we're going to want to sketch 2 periods or 2 cycles. The amplitude is the absolute value of A, which is the absolute value of 0.09, which is, of course, simply 0.09. The period is 2 pi over B, which is 2 pi divided by B is 5,200 pi. So 5,200 pi. Well, the pi's cancel, and we get 1 over 2,600. That is awfully, awfully small. That's approximately 0.0004. However, it's said to sketch 2 cycles. So 2 cycles. We're going to do 0.00. I'm going to use decimals for this one, and why not, as opposed to those fractions. It is approximately 0.0008, which of course is 2 over 2,600 or 1 over 1,300. Okay, you got our information. Let's do a sketch. All right, we know that our amplitude is a whopping 0.09 meters. Wow, that's pretty small. So 0.09 here, go down the same distance, negative 0.09. And we know that the period is 4/10,000ths. Oh my goodness, well I'm obviously going to adjust my scale. I'll make this 4/10,000ths. We know that's the same as 1 over 2,600. We want 2 periods, so I'll go out the same distance. 2.008, which is the same as 1,300th. Okay, it's a sine, so we want to draw a period and then another period between these two. So up, down about halfway, and then back to here. That's 1 period. And then up to 0.09, down through the middle, and back here. That's the 2nd period. We could, of course, stretch a little bit or do whatever, but I just try to kind of do my scales that way. And you can check that one with Desmos if you'd like to. So there you have it. Some simple harmonic motion graphing simple harmonic motion, knowing what we know about trigonometric graphs.